Hello friends, today we are going to discuss some concepts in thermodynamics. As thermodynamics is an important part of physics, I am your host and companion for today, Dr. Abhinav Bhargav, currently working as Assistant Professor in Faculty of Science, the BSSS College, Bhopal. So today we are going to work out on some of the basic concepts that will develop an understanding in your mind how we should pursue thermodynamics in our basic semesters of BSc. So let us start with the plan of talk. In the plan of talk, we have a discussion about a brief history of thermodynamics. In historical background, we are going to discuss the contribution of the scientists who have provided us a platform to discuss the thermodynamics by indigenous concepts. Apart from that, following our plan, we will be having thermodynamical systems and its types. In this thermodynamical systems, we will be discussing three types which are contributed to this thermodynamics using certain processes which we observe in our daily life. Again, following that, we will be talking about thermodynamical coordinates that are necessary to give the state of a thermodynamical system. Whenever you are going to explain a thermodynamical system, the equipment you have in your hand is the thermodynamical coordinates. After that, we have a very basic concept of path function, point function, which can be correlated with many terminology used in thermodynamics, and it is going to be very fascinating for you. Then we have the work done by and on a thermodynamical system. We have these processes going around us which are involved with different kind of other type of work which can be on the system, which can be by the system. Here we are going to discuss the major part, that is work done by or on a thermodynamical system. And that next topic will be followed by internal energy of the system. That is the basic concept everybody should understand, whether he will be a science enthusiast or not. But that is important for each one of us to understand what is the internal energy, because that energy does not even confine itself to physics, but it is confining itself to the entire universe. So the last topic of my talk will be reversible and irreversible processes. These processes are around us, but we need to designate them with a well systematically defined definitions. So we are going to discuss that in the last part of this presentation. So let us talk about the historical background. I am proud to mention that a professor named Meghnad Saha contributed a great equation to the ionization process. In 1920, Indian scientist Meghnad Saha proposed ionization equation which relates the ionization state of a gas in thermal equilibrium to the temperature and pressure. This equation is one great correlation between quantum mechanics and statistical physics. Followed by Meghnad Saha, there is one pioneer professor who studied the particles and propounded a very famous theory known as Bose-Einstein statistics. I am proud to announce his name. In 1924, Indian scientist Satyendranath Bose developed statistics for indistinguishable particles in statistical physics with the great scientist Albert Einstein, which is called Bose-Einstein statistics very famously. This statistics is applicable to the particles who do not follow Pauli's exclusion principle. This Pauli's exclusion principle is followed by the electrons, our good friend, and the particles which do not follow this Pauli's exclusion principle are known as bosons in the name of the Professor S.N. Bose. Photon is a great example of this boson, and other examples are mesons. Now moving to the first concept we are going to discuss in this video, in this presentation, that is the thermodynamical system. When we talk about this thermodynamical system, you may encounter different types of definitions. And today we are going to distinguish these definitions and their explanation very beautifully, and that will help you to understand them very carefully. So let us talk about the first definition. A thermodynamic system is defined as a quantity of matter which is a space of interest. That is an interesting thing that we need to discuss in this subject, and this will provide you a more deep learning and good effect of the theories. The mass or region outside the system is called the surrounding. As we have this outside surrounding, this is the same surrounding around that system. If I am the system, then this skin you can see is the boundary and the outside system is the surrounding. Inside me there are different properties, and that are, when thermodynamical defined, can be contained in this particular topic. and the surface that separates the system and the surroundings is the boundary. As we have this example, you can see through this diagram, we can have this work heat interchange with the surroundings and the system, which is majorly known as thermodynamics. We have some definitions with system boundary. A boundary is a closed surface surrounding a system through which energy and mass enter or leave the system. I think that is a correlated general phenomena applied to lot of other theories, other process also. Surroundings, everything that interacts with the system. So we have this surrounding, and this surrounding is interacting with us. If it is cold outside, we will feel the cold inside also. If it is cold inside, you will feel that you need some warmth, and you may get yourself into the sunlight to feel that warmth. That is the power of the surrounding. System can be anything you see and observe around us. That is, you can see ourselves as system. You can see the process going around you, like you make a tea in the morning. That is a process called thermodynamic process. But you need some good definitions to understand that process, and through this presentation, we are going to understand those topics. Moving to the next definition we are going to discuss a thermodynamic system is a body of matter and or radiation considered as separate from its surrounding and studied using laws of thermodynamics. In this definition, we are going to distinguish the definition of thermodynamical system according to the three systems. We have this isolated system, closed system, and open system. We will be talking about these definitions in the further slide. Let us talk about some more definitions associated with thermodynamics. So, thermodynamic system means such a macroscopic body which is made up of large number of microparticles such as molecules, atoms, ions, etc. As we already know that we all are made up of certain type of mechanism called cells, tissues, organ system. In the same way, the material, the elements, the objects we observe around us are made up of microparticles, and whose state depends on thermodynamic quantities like temperature, pressure, volume, and entropy. These are going to be your weapons for understanding the thermodynamics. So let us consider these weapons as the most important part of this entire theory. Moving to the next part, we are going to discuss the types of thermodynamical system. When we discuss these types of thermodynamical system, the first and favorite system for me is the open system. Open system is very easy to understand. It contains a simple definition that in the system, when mass and energy can both be transferred, both can be exchanged, that is known as open system. We have this diagram on the right side. You can see that in this body, in this open system, mass can come in and mass can go out. Energy can come in and energy can go out. There is no restriction on the movement of mass and no restriction on the exchange of energy. Example, a steam turbine, a pool filled with water where the water can enter or leave the pool, or in general we can have another example that can be a tea, cup of tea which is open and kept outside for you. That tea is exchanging the vapor, and that tea is also exchanging the heat with the surrounding, and the tea gets cold if you don't consume it at an appropriate time. Talking about the next system, we have the closed system, a system which has the ability to exchange only energy with its surrounding and cannot exchange matter is known as a closed system. So this system is rather more easy. You can understand that we don't allow the mass to flow outside, but we allow the energy to flow outside. We allow the outer energy to come inside. This is simply the definition of closed system. What is an example? A cylinder in which the valve is closed is an example of a closed system. When the cylinder is heated or cooled, it does not lose its mass. Or another example in context of the same tea which we discussed before, it is you keep a lid on your tea. You may see that the vapor will not exit the tea. That means there is no exchange of mass is taking place. But at the same time, after some time, your tea may get cool. That means energy transfer is yet possible right now. This is the perfect example of closed system. What next? What next we have is the isolated system. This isolated system is of very interest, and you have this isolated system accompanied by you daily in summer season and winter season. I am sure the example will fascinate you. With this you can learn how this system is accompanied by you and how this system works. A system which cannot exchange matter or energy with the surroundings is known as an isolated system. So that is very, very simple. It does not allow the energy to flow. It does not allow the mass to flow. The best example, it is also mentioned here, the systematic example are reactants are present in the thermos flask or insulated vessel. The same thermos flask you carry in the summer season when you need hot water instead of cold water. When you need cold water instead of hot water, you pour your cold water into this thermos flask, you carry it with you, and the flask keep it cool for the entire day. That means it does not allow the mass to come out, it does not allow the coldness to go out, or we can say that no exchange of heat is possible in this type of system, and no exchange of mass is possible in this type of system. So this type of system is particularly known as isolated system. So going to the next thing which we need as a weapon to understand the thermodynamical system, we have the thermodynamical coordinates. We will be defining these thermodynamical coordinates one by one. Before that, we should see what is the perfect definition for these thermodynamical coordinates. The physical quantities that are required for description of thermodynamic state of a thermodynamic system are called thermodynamical coordinates. As the name suggests, coordinates, when talked in terms of Cartesian coordinates, it allows us to understand the position of a particular thing in corresponding to the three axes x, y, z. But in thermodynamics, these x, y, z are not the system we use. We use a different type of coordinates which gives the information about the state of the thermodynamical system. These are the temperature, pressure, volume, and entropy. Let us consider an example that the gas is filled in a cylinder and it is expressed by these terms, and its state can be explained in a better manner by using these terms. Hence, temperature, pressure, volume, etc. are the thermodynamical coordinates of a system. Why we need this system? We need this system to understand the physics around us. Why we need these coordinates? To more elaborate these systems, to more understand these systems, we need these coordinates. So let us define these coordinates one by one. Temperature. Temperature is something that is known to you very well, but let us define it more systematically. Temperature is the measure of hotness or coolness expressed in indicating the direction which heat energy will spontaneously flow. That is, from a hotter body to a colder body. It is obvious that one thing which is kept at hot temperature or higher temperature, considered as hot body, when connected to a colder body which is at lower temperature, the heat transfers from the hot body to cold body. Moving ahead, we have this pressure. Pressure is something which is not available only physically, it is also available mentally. And we are here to reduce that mental pressure. So what is the definition for pressure? Pressure is defined as the physical force exerted on the object. The force applied is perpendicular to the surface of the objects per unit area. The basic formula for pressure is force upon area. That is the basic formula we have known from a long time, but in this thermodynamics you are going to face some new formulas which will be very fascinating for you. And the unit is Pascal for this when we use it generally. Now moving ahead, we have the volume. Volume is something which is occupied by us. Volume is something which is occupied by the things you pour into your hard work. You pour into your mobile, you pour into something which can assist these volumes. So every three-dimensional object occupies some space. This space is measured in terms of its volume. Volume is defined as the space occupied within the boundaries of an object in three-dimensional space. It is also known as the capacity of the object. Moving ahead, we have the entropy. Entropy is something which is going to be very broad in the upcoming presentations, upcoming topics. We are going to discuss it very fascinatingly in different ways, using different type of phenomena, using different type of concepts. Here the entropy, I will be defining it very simply. It is a measure of the disorder of the system. It is an extensive property of the thermodynamic system, which means its value changes depending on the amount of matter that is present. In equations, entropy is usually denoted by the letter S. Entropy is simply said as the degree of disorder. Whenever you see the disorder, if there is increment in disorder, that shows that entropy increases. When there is a faculty which comes to the class and makes the class ordered, the entropy of the class decreases. This is the more generalistic approach to define entropy. Let us come to the next concept, the concept of path function and point function. point function is also known as state function, a property whose value doesn't depend on the path taken to reach that specific value is known as state function or point function. So as the name suggests, point function depends on the point, not on the path. What are the properties of a system at a particular point? That instantaneous definitions will be helping to define point function. So let us see what is state function or point function in more systematic manner. Point functions are the values which depend upon the state of the substance, like temperature, pressure, or the amount or type of that substance. As a matter of fact, state functions do not depend on how the state was reached or established. They are not process-based things. These are the target-based things. So here we see the target, that is a point actually, and we don't see the process. Moving ahead, you have this path function. A path function is a function whose value depends on the path followed by the thermodynamic process, irrespective of the initial and final states of the process. So it is not necessary from which point the process started, it is not necessary on which point the process will end, it is only dependent on the path it followed. So to explain this, I have a beautiful example. Let's talk about this. The example of path function is work done in a thermodynamic process. Work done in a thermodynamic process dependent on the path, not on any point. Let us see one diagram. In this diagram, we have this pressure on y-axis and volume on x-axis. This graph shows there are three processes going on by the name A, B, C. In the given PV diagram, we can easily say that for the same initial and final states of the system, work done in all the three processes is different. For process A, work done is B2, A1A. For process B, the work done is B2, B1A. For process C, work done is B2, C1A. The starting point and the ending point is same for all the three processes. That means the point function will be defined at the position 1 and 2. But the path followed will be different for all the three processes, that we can mention it as path function. Another example of path function is the heat. Heat is actually a path function. So how do we consider these two things and how do we compare these two things? I have a tabulation that will make you understand the comparison between these two. Point function, its values are based on the state of the system. Example, that is pressure, volume, temperature, etc. Path function, its values are based on how that particular thermodynamic state is achieved. Point function, no matter by which process the state is obtained, its values will always remain the same. It is not a matter of process for point function. It is a matter of process when we talk about the path function. Different processes to obtain a particular state will give us different values. In point function, only initial and final states of the process are sufficient. I think that gives the point function data, that is the starting point and the ending point. But we need to know the exact path followed by a process in path function. In point function, its values are independent of the path followed. In the path function, its values are dependent on the path followed. It is an exact or perfect differential, the point function. It is an inexact or imperfect differential when we talk about the path function. Its cyclic integral is always 0 when we talk about the point function. Its cyclic integral may or may not be 0 when we talk about the path function. It is the property of the system. What? The point function is the property of the system. Path function, it is not property of the system. Its examples, when we talk about the examples of point function, that is very easy to understand, that is density, enthalpy, internal energy, and we have this entropy. When we talk about the path function, its example are heat and work. So here we are going to discuss about the more and more topics which are going to define this thermodynamical concept. The next concept is work done by and on a thermodynamical system. So when we are going to discuss this, work done is by the system or on the system. We have to define it in two types. One is external work, while if we work done by one part of the system on another part of the system is known as internal work. Here we are going to discuss the external work. So to calculate the external work of a thermodynamical system, we have to consider a cylinder with movable piston filled with gas. Cylinder is made of conducting material, that is exchange of heat from surrounding is possible. Initially, the piston is pressed by keeping some weights on it. then gas is compressed. It is obvious if you want to press something, we have this gas and piston setup, we need some weights so that the piston should move towards the down position. In this way, work done will be on the system and the gas will get compressed. That means volume will reduce and the pressure will increase. So work is done on the gas. In the next, if weight is removed, it is obvious that every action has equal and opposite reaction. The reaction will be the gas will expand and that will move the piston upwards, increasing the volume, decreasing the pressure. So in this, we will consider that work is done by the gas. Now, using these two things, we can show a diagram which will help you to understand that what is the variation of pressure and volume when these processes take place. That is the PV diagram. You can see that from 1 to 2, in the expansion process, the volume increases, but at the same time, the pressure decreases. And the area below this curve gives the work done. So we will do a small derivation to understand what these values possess in more systematic approach. Let us see. We have let the initial volume and pressure of certain mass of gas filled in the cylinder be V and P respectively. If area of cross section of piston is A, we will consider that, and then force exerted on the piston by the gas in state 2. I think everybody is able to understand this state 2 is this one where the work is done by the gas and there is expansion taking place. Since we can see the piston is moving upwards, the volume is expanding, at the same time the pressure is decreasing. So we are going to define the force. What is force? Force is pressure into area. I think that is quite easy to understand. That is the basic formula we know for pressure. Pressure is equals to force upon area. Force will be equal to pressure into area. I think it is mentioned here and it will be clear to everyone. So we have taken the same details on the next slide. Let us move further. We have due to this force, if the piston is displaced by a distance dx, so this is the important quantity we need to remember, outwards, then work done by the gas in this expansion is dW is equals to F into dx. That is the simple formula for work done, force into displacement. Next, we are going to discuss another thing. Let us see. What is the force formula we assumed? That is P into A into dx. This is in this step you can see. Then what is the further process we will see? That is A into dx is replaced by a term called dV. What is that dV? dV is actually change in volume and that is represented by A into dx and that is the increase in the volume of the gas. Further, thus if the volume of the gas increases from V1 to V2, V1 is the previous condition, V2 is the final condition, then total work done on the gas will be W is equals to integral from V1 to V2 dW. Therefore, W will be equal to integral of V1 to V2 and we substitute the value of dW, that is PdV. This equation represents the work done by the system. Similarly, when the piston is pressed, gas gets compressed. So that is the volume of the gas decreases, work is done on the gas. For that, W becomes a negative. Why it becomes negative? Because we are spending our work on that system. When we are doing work done on the system, we are spending our work on that system. When something is spent, it is negative. So that's why the work done in the process called work done on the system will be negative. That is W equal to negative of V1 to V2 integral P dV. Let us now move to the internal energy of the system. This is something, as I said, which is a part of this universe. What do you understand by internal energy? Let us define it. Each thermodynamic system has a fixed amount of energy which is due to the motion of molecules of the system, distance and force of attraction between them. This is called internal energy of the system. To conclude it more in a simpler manner, I will define it in two parts. Let us see what are the two parts. There is another definition presented on the video. You can see that definition, you can use that definition. Let us move to the two parts. There are two types of internal energy of a system. We all know that there are molecules moving inside the system, and when these molecules are moving inside the system, they possess energy. We know it as kinetic energy. So the first energy will be internal kinetic energy represented by the term UK. And the second type of energy will be the force that is working between the two type of molecules, two atoms, two interactions. That force of attraction or repulsion, we will name it as internal potential energy associated with that force, denoted by UP. What is the total internal energy? It is the sum of UK plus UP, as you can see. So this is the total internal energy. So now we are going to discuss about reversible and irreversible process. As you can see on the screen, there is one graphical image format pertaining, that is making you understand how you do certain process and how they are reversed. So we are going to discuss that further. So reversible process, the process which can be completed in reverse order, as in exactly the same states it was completed in direct order. So when we do a process, there is a possibility we want to reverse that process, but the state should not change. If the states are changed, that means the process will not be considered a reversible process. So keeping the states constant, doing one process in forward direction, reversing that direction and doing that process, and if it is completed successfully, it is considered to be reversible process. Another definition for reversible process: a reversible process is a process in which the system and environment can be restored to exactly the same initial states that they were in the before the process occurred. If we go backward along the path of the process, so this is the better definition, I think. A more elaborative form of the discussion we already did. Now, what is important note in this particular process? It is quite easy to restore a system to its original state. The hard part is to have its environment restored to its original state at the same time. Because of this fact, you are going to recognize that this reversible process are imaginary and there is no 100% reversible process. So examples of reversible process is, still we have some process which are nearly reversible. We will consider them as example. One is extension of springs. Another is slow adiabatic compression or expansion of gases, the frictionless motions of solid, and you may have certain examples other mentioned here. Following that, we have this irreversible process. Irreversible processes are the majority of the process you see around you, and it is very easy to define them. In contrary, if the process cannot be completed in reverse order as exactly in the same states in which it has been completed in the direct order, then it is called irreversible process. That is very easy to understand. You cannot reverse the process, the state will change, the process will be categorized as irreversible process. Another definition: an irreversible process is what we encounter in really at almost all the time. The system and its environment cannot be restored to their original states at the same time. This is what happens with us in our life also. You can correlate this with your life and its process also. Because this is what happens in nature, it is called a natural process. So what is the better name for a irreversible process? It is the natural process. What are some examples? Before that, let us talk about important note here also. In reality, almost all processes are irreversible, and some properties of the environment are altered when the properties of the system are restored. This is the natural phenomena. This is the fact which we encounter around us. So what are some examples? We will see some examples like relative motion with friction, heat transfer, diffusion, and some more other examples mentioned here. So coming to the last part of this presentation, this video, we have this condition of reversibility. We need to know what conditions are necessary to be known to us when we talk about these processes. Let us talk about the necessary conditions for any process to be reversible: that there must be no loss of energy of the system due to friction, viscosity, etc., and by conduction, radiation, convection, etc. In short, we should have no loss of energy. And in any process, we know there is always some loss of energy, whatever we do. Now the second point, there must be extremely slow variation in pressure and volume of the system. However, that is not in our control, so that the system remains in thermal equilibrium in all the states in between these processes. That is also not possible. So that's why when we talk about reversible process, those are considered as imaginary process. Actually, no process can follow perfectly the above conditions, because in any process there is some loss of energy due to above reasons, possibly energy. Thus in practice, perfectly reversible process is not possible. This is an ideal situation. Actual processes are usually irreversible. This concept is very important in thermodynamics. I think that is correlatable with all the things you do in your life. Our life is also process, the learning is also process, and when we learn, there is always some losses. not of the energy, but may of the knowledge. To contain that knowledge, I am here and we are working on the concepts of thermodynamics. So last point, this concept is very important in thermodynamics. On this basis, the scientist Sadi Carnot imagined an ideal heat engine in which there is no loss of energy. And I am also presenting a comparison between reversible and irreversible process, that is for you to boost your knowledge. So I think the knowledge we studied today is going to be a power for you. You will be learning it and you will be using it to get some good academic marks. And today this is enough, and now we are going to discuss the further part, that is the next part we will discussing will be entropy. This is Dr. Abhinav Bhargav, Assistant Professor, Faculty of Science, the BSSS Bhopal, leaving you all for the next part.